Hey everyone, welcome into this lecture. In this video we'd like to talk about the derivatives of the hyperbolic functions. So let's start by remembering our function formulas for cosh and sinh. Recall that cosh of x is equal to 1/2 e to the x plus e to the minus x. It's like an average of e to the x and e to the minus x. And sinh of x is equal to 1/2 e to the x minus e to the minus x. And then the other four hyperbolic trig functions are built the same way that we would build the trig functions. They are done by tange of x, tangent hyperbolic, tange of x is equal to sinh of x divided by cosh of x. And from there we just get all the reciprocal functions, right? So cotange of x is equal to 1 over tange of x. Secant, hyperbolic secant of x is 1 over cosh of x, and cosecant hyperbolic cosech of x is 1 over sinh of x. All right, now you don't have to say these names of these functions this weird way, but for me, it's just easy. It's easier for me, so you can say these. I didn't make these up, okay? These cosh and sinh and tange names. So let's compute the derivatives of these things so that we have the derivatives. And as we know, the fundamental theorem of calculus says once we know the derivatives of these, we will have antiderivatives of some other functions, whatever we end up with. So let's start with cosh. We want to take the derivative with respect to x of cosh of x. And of course, the way we're going to do it, and the reason that we have this formula at all, right, is for computational reasons, because we have a nice geometric definition of what it means to be cosh of x. But it's easier for us to take the derivative of something involving exponential functions. Derivative is linear, so this becomes then just 1/2 times the derivative of e to the x plus e to the minus x. All right, and these derivatives we can take individually. We get 1/2 times derivative of e to the x is itself. Derivative of e to the minus x is minus e to the minus x by the chain rule. And as we look at this, we took the derivative of cosh and we got the formula for sinh, right? And so that tells us that the derivative of x with respect to x of cosh of x is equal to sinh of x. All right, let's take the derivative of sinh now. So, by the way, this is close to what we get with regular trig, but it's not quite equal, right? Because the derivative of cosine is minus sine. All right, so here now we want to take the derivative of sinh of x. We're going to do it the same way. All right, the derivative of sinh is going to be the derivative of that formula, right? 1/2 e to the x minus e to the minus x. And same thing happens, right? We can take out the 1/2 and individually take the derivatives of these exponential functions. And what do we end up with? 1/2 of e to the x, derivative is still itself, right? Derivative is e to the x, minus derivative of e to the minus x. So that's going to become minus negative e to the minus x. That's plus e to the minus x. And of course, this is cosh, right? So the derivative of cosh is sinh, and the derivative of sinh is equal to cosh of x. Okay, and so these two functions, when you take the derivatives multiple times, they just keep going back and forth, right? Derivative of cosh is sinh, derivative of sinh is cosh, and this is a pattern that repeats on a cycle of 2. So every other one. All right, let's take the derivative of tange now, and I'm going to let you guys do these 3 as exercises, but we'll do this one together. So derivative of tange. Let's see how we're going to do this. This one doesn't, there is a formula. You could easily write down the formula. Derivative of tange, I'm going to do, because we know the derivatives of cosh and sinh, I'm going to do this as the derivative of the ratio, sinh of x divided by cosh of x. This is the definition. All right, and when we apply the derivative to this, we have to obey the quotient rule, right? So the quotient rule says we should take the bottom function, cosh of x, multiplied by the derivative of the upper function minus the upper function times the derivative of the lower function, and then divide the whole thing by the lower function squared. I'm writing out all the details here. but it should be pretty straightforward, right? So cosh of x squared. And so what do we end up with? Well, derivative of sinh is cosh, right? And so this first term ends up being cosh squared of x minus the derivative of cosh is sinh, so this is then sinh squared of x. And this is all over cosh squared x again. And now we want to remember something about the geometric definition of sinh and cosh. And these are called hyperbolic trig functions because they came from a unit hyperbola, right? And we built this unit hyperbola in such a way that the defining equation of these hyperbolic trig functions was exactly this, right? That cosh squared of, we called it tau in the last lecture, but cosh squared tau minus sinh squared tau had to equal 1 for all tau, so therefore for all x as well, right? And so this is the defining property of these hyperbolic trig functions, and that's exactly what we have here, right? And so this just ends up being 1 over cosh squared of x, but just like with regular trig, 1 over cosh of x is actually secant, right? Hyperbolic secant of x, and so this is hyperbolic secant squared. And again, this is not a coincidence, right? Or it's not unfamiliar, I should say. The derivative of tangent is secant squared. The derivative of hyperbolic tangent is hyperbolic secant squared. Now, we have to be careful. You can't just assume that all the formulas are the same. And I want you to work some of these out here, all the rest of these out, these last three. Some of these will be slightly different, but what will be different is just like with cosh here, they might differ by a minus sign. Okay, they might be the opposite sign of what you expect. All right, but that's how you take the derivatives of the hyperbolic functions. So I'm going to leave this one here, and I'll see you in the next lecture.